So this is section 4.2, the definite integral. And the word definite is going to be very important because in the future we're also going to see indefinite integrals. So this builds on what we were talking about in section 4.1 with Riemann-sum rectangles that add up the area underneath a curve. Let f be a function defined on an interval where you divide that interval into subintervals, all of equal width. We let this x1, x sub 1 asterisk be any sample points. Then the definite integral of f from a to b is, and this is actually from the last section, it's the limit as n goes to infinity of, I'm using my sigma notation here, I equals 1 to n of f x 1 and then asterisk change in x. So this is just the addition of an infinite number of rectangles underneath the curve. The way that is defined is using this notation, which is what is brand new. So we have this, which is called the integral sign. Literally, that's what it's called. And the bottom and the top are your limits of what we call limits of integration from a to b. And then we put our function inside. And then we use that differential that we used way back, dx. So the idea here is to note that if you were to take the limit of an infinite number of rectangles under a curve, that is the same as what you see on the left-hand side, the integral of the function from a to b. The dx essentially to us is telling us what we're taking the integral with respect to, that the variable that we're dealing with inside is x. And we can do this provided that the limit exists, that there is a limit. You can take an infinite number of rectangles. If so, we say that f is integrable on a to b. So after we've talked about differentiation, taking derivatives for a long time. That was the first big chunk, basically the first half of the semester. And the second half here is integration. And there's a very direct relationship between differentiation and integration. We saw some of that in section 3.9, and then we started in 4.1 seeing what it means kind of graphically, other representations of it. And then now we're going to talk more using this new notation. So as you can see, the symbols that I used above are here again. So I'll just write this again. This is the integral sign. And the a and the b are limits, like I said, of integration. So they're just telling us what we're integrating over, what interval we're integrating over. And as I already mentioned, this here is considered independent variable is x. The reason that you may need that is because if you're planning on taking higher level calculus, you might end up, you do not need to write this down, but you could end up with a multivariable function, and maybe you would actually have to do something like this. So this is multivariable calculus. And you can see that in that case, you're going to integrate with respect to one variable, and you're going to integrate with respect to another variable. So it's important that we have this here to tell us things. And what you should understand is it's essentially related to that delta x that you see when we're doing the rectangles, that change in x. And if you remember from differentials, dx is equal to the change in x. And so that's the idea behind rewriting it in that way. So let's look at an example of kind of the main idea of this again, which is the idea of the Riemann sum. We're going to do it with n equals 4 for this function on this interval, and we're going to do something using the midpoints. So in the section 4.1 we looked at the left hand side and we looked at the right hand side, Another way to do a Riemann sum would be the midpoint. So you'd have your interval, 4 intervals in this case, and you're actually going to look at the midpoint of each interval. So graphically, that would be something like here, 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 and here. And then I can show it on the last example here, would be the easiest first. So I draw the line here, and that's the height of that rectangle. And what you should notice is that this is actually going to get us a little bit closer, because on one side, it's essentially underestimating, but on the other side it's a little overestimating. So this can often be a better estimator of a function using that midpoint rule. There's also something called the trapezoidal rule. You may see that at some point. Okay, let's see. So that's going to go all the way to here. I'm just trying to look at there we go. Okay, it's going to come down here. No. All right. Okay, and then this one so the height is wherever that midpoint is. That's the idea. So it's over, and then it's over here, like that. Yours is probably going to be better than mine. And then the last one here, I'm going at the midpoint, that's my height, and you can see that that one actually looks pretty good. So you can see that this area that we find is going to be pretty accurate, but still an approximation. Okay, so notice it's using the asterisk because this is not left hand or right hand, it is the midpoint. So the way to just think about this is that the width of each one of these is still the 0.25, because you still have 4 intervals here, and they're still each 1/4. So it's still the idea of the change in x is b minus a over 4, so 1 minus 0 over 4. We still have that. The difference is the height, so this is my point is this is my delta x. But now I just need to think about what the heights are. So in that case, the first height is basically a half of a quarter. Yes, a half of a quarter, which is an eighth, because it's sitting right here. So it's halfway between 0 and 0.25. So what you could do is you could add up 0 plus 0.25 and divide it by 2, which is 0.125. I'll do the rest of them as decimals, just to show you that as well. So the halfway point here, the height of that rectangle is halfway between 0.25 and 0.5. So you can add them together and divide by 2. 375 is what you're going to get there. And then my third rectangle is halfway between 0.5 and 0.75. So that's 0.625. And then my last height of the last rectangle there is halfway between here, and that's going to be 0.875. Okay, so, and I don't know if you really want to see the first one in you want them all to be the same, if that drives you crazy, which sometimes, some people, it does. So this is 0.125, so just half of 0.25. And then the idea here is the function is the cosine pi over 2x squared. So you'd be putting your values into your f of x, making sure you're using radians. And that's going to give you 1/4 times, and you can check this and make sure you get the same numbers here. You'd get that, you'd get 9757 and 8176 and 0.3599. And you add those together and you're going to multiply by the 1/4, so you add them together, 3.1529 and 0.7882. So basically this is just, again, just another approximation that I want to mention, the midpoint rule. In the future, the idea is we're going to find this exact answer by using this notation here so this would be the integral from 0 to 1 of cosine of pi over 2x squared dx. And that would give us the exact answer. That would be that limit of, say you did an infinite number of midpoint rule rectangles, you would be getting this same answer by doing this. Now you might be like, well, what is this? Well, we'll be talking about that soon. Okay, so a couple notes here. If you have a function that is integrable, and if the function is always positive, greater than or equal to 0, so the y values are always 0 or above, on that interval, then the area under the graph of f over the interval a to b is given by this. So this is just the big idea that you can find the area under a curve by doing what's called integration. Okay. Now, if x has negative values, so let's, sometimes it's not these perfect, functions that always sit above the x-axis. So if f has negative values, what this gives you, and it looks like I cut it off just a little bit, sorry about that, gives you what's called the signed area. And that means what it's going to do is it's going to take the area above the x-axis and that's going to be positive. The area below the x-axis is going to be negative when you integrate it all at once. And so you're going to get the signed area because it's not total area. It's the area with the negative area subtracted. So in this case, the signed area that you see there, it's going to be A1. You're going to subtract the A2, and then you're going to add the A3 is the idea. Like if you were to integrate it, that's what it would give you. All right, and the reason for that is sometimes we want total area, so we actually have to split it up into pieces, and we'll see an example of that. So if f is continuous on some interval, then you can integrate it on that interval, and of course that's very important because it allows us to do things with continuous functions that are continuous. Now remember, a function that is continuous is not necessarily differentiable at every point. But this is saying if a function is continuous, it is in fact integrable at those points. Okay, so now you're like, oh, I thought we were done with our sigmas. Well, this limit as n goes to infinity, this is, a function here inside the sigma. When it says represent this as a definite integral, the idea is just rewrite this using integral notation. And when we say definite integral, that's because we're integrating over some sort of interval from a to b. That's the idea of definite. It's because we're told from here to here. Okay. So all we have to do is think about our limits of integration, and that's from 1 to 5. So nothing there. That's too exciting. We're always going to have the dx talking about the independent variable that we're dealing with. I mean, sometimes you might have dt or I don't know. Typically it's dx and dt is what we see, but arguably you can have anything, is just depending on what variable you have inside. And then the inside of this is just going to be this piece written with the variable x. So the idea of sine x over 1 plus x. So that's just how to change it, and you can go back to the first thing that we had on the first slide to see that those two things are equivalent. Except that this one does not require you to add up an infinite number of rectangles. All right, so let's use the definition to find the answer to this. Okay, so idea behind this is, and I'm going to start, I may need a little bit more space, so I'll just kind of start it up here. Okay, so let's take a chapter from the last section, like some of the information that we got in the last section. So we'll think about, in this case, let's start with delta x, which is b minus a over n. So the idea here is b minus a, because it goes from 1 to 4, over n is just 3 over n. Okay. And we're using n because we're talking about the idea of that definition from the first page, where we're looking at the limit as n goes to infinity of all these rectangles. So now I'm just creating this general idea of, we're using n, and then what happens as n goes to infinity. Okay. And then that means that our sampling points are coming from the beginning of the interval A, so A is 1, plus, and then if you remember from the last section, all we're doing is taking a bunch of however wide that interval is and multiplying it by I as we go along to get the different sampling points. So this was similar, and if you want, you could write it like this, just depends if that's what you like. Okay, so the idea here is now I'm going to rewrite this, and I'll probably do a line here and then I'll head down, so don't worry about this, just pretend that's not there. All right, so the limit as n goes to infinity, and then remembering from last section, we're going to take the sum as I goes from 1 to n, okay, and we're looking at the limit as n goes to infinity, of the sampling points 1 plus 3i over n in this function. So notice 1 plus 3i over n squared, because that's here, okay, so I'm replacing x with my sampling points, minus 3, that's it, and then of course times the change in x, your delta x, so 3 over n. And then all we're going to do now is just like we did in the last section, which is multiply this out and then replace the I with what that summation is, which are properties that we were given when we talked in section 4.1 about sigma notation. Okay, so let's come down here. Limit as n goes to infinity. And one thing you could do, and you know that, well, you know what, maybe I won't do it. You can bring out the 3 over n if you want. I'll just leave it in this time to show that. Okay, so what I'm going to do is I'm going to multiply out my 1 plus 3i over n, because it's times itself, it's squared. So I'm going to have 1 plus 6i over n plus 9i squared over n squared. So that's just taking this and squaring it, that binomial, minus 3 times 3 over n. Okay, so just due to spacing, that's why you're seeing this down below instead of next to it. But we'll look at same limit, but now I'm going to actually do my summations, and I'll leave the 3 over n on that outside. So we have 6i over n. So summing the I gives us n times n plus 1 over 2. So that's going to give us this. So I replaced the I with the summation of I from 1 to n, which is n times n plus 1 over 2. And then I'm going to replace the I squared with the n times n plus 1. Ooh, it's kind of far. It's kind of far away. All right. N plus 1, and then 2n plus 1, and this is over, okay, this is over 6, but we have 6, and then we have an n squared in the denominator, so that's coming from right here. And then we had the 2. So we had 1 minus 3, so that was a minus 2. So when we sum that, it's going to be a minus 2n, because any constant summed from 1 to n is multiplied by n, because you're basically just adding up a bunch of minus 2's every single time. All right, and then we have our 3 over n over here. All right, so now I'll come down again. So I have the limit as n goes to infinity. We're almost there. Now we can kind of think about what we get when we, you know, do these with the 3 over n on the outside. So I'm just trying to think of the best way to write this here. Okay, so you're going to see that these n's simplify, that we end up with 6 over 2, which gives us 3, but we're multiplying by 3 over n. So we're going to have 9 times n plus 1 over n, because I'm multiplying by 3 over n. Okay, now, ooh, it gets tricky. Okay, now over here, we're going to have this n that simplifies with this n, The 9 and the 6 simplify, so we'd have 3 in the numerator and 2 in the denominator, but the 3 in the numerator gets multiplied by this 3, so that's going to be 9, and then n plus 1, 2n plus 1 over, and then we have that 2 here, and then that gets multiplied by the 3 over n in the denominator, so 2n squared. And then the minus 2n gets multiplied by 3 over n to get a minus 6. Okay. Now, due to spacing and certain limitations here, I'm just going to talk to you about this limit because we've talked about it in the last section. But we want to remember that this limit, n plus 1 over n, because of the same exponents, goes to 1. So this is going to give you 9 when you take the limit. Over here, understand that this leading term, if you were to multiply out this piece here, because all you really care about is what that leading term is, it would give you an 18n squared. That would be the leading term. When you take that limit over 2n squared, you're going to have plus 9. So the key thing to see is the exponents are the same, like they have the same exponent, and so like highest degree. And so when you take the limit, you're just taking the ratio of the coefficients. And then we still have our minus 6 over here because we did not lose that. And that's going to give us 18 minus 6, or a 12. So the idea here is what we just did was use the limit definition to add up every single rectangle, like an infinite number of rectangles, underneath the curve of x squared plus 3. So you could kind of picture what x squared or x squared minus 3 looks like. So x squared minus 3. And what would happen if we added up all the rectangles between 1 and 4. So that would be some above and some below the axis. And overall, you would end up with an area, because that's what it is, of 12. It's just a lot of work to get there.